All right. So in next section in shortest path is Floyd-Warshall. So far, whatever we talked about in shortest path, the problem statements were like that you are given a source, or somehow you could figure out that which one the source is, and we were able to come to the answer from that given source, finding shortest distance either to one target or all the nodes in that graph. Find the shortest distance to all the other nodes from the source, and then we were able to give the answer. Now things will change a little here. Let me come to that. So imagine that the same graph is given to you, but somehow question is formed such a way that you cannot answer it until you know the shortest distance from every node to every node. By that I mean that to answer the question, I should be knowing what is the shortest distance from A to C, what is the shortest distance from A to D, and what is the shortest distance from A to E, right? Most of them. Same goes for what is the shortest distance from B to C. If there is any route from B to C, then what is the shortest distance from B to E? Only after I know all of this, then only I'll be able to complete whichever question is given to me. So this is a category where we say that I should know all pair distance. All pair. You have to calculate all pair distance, then only I'll be able to conclude the answer. Let's just see one of such question first. So here is this one question which is talking about find the city with smallest number of neighbors at a threshold distance. So in the same graph which we are having here, imagine that they are saying that find the city, which our answer is, which is having smallest number of neighborhoods. So let's suppose from A to B you have 5 as the weightage or distance, whatever you can call it. From B to E 6. Same way, all the edges are having some weight given, right? Now if you are given a threshold, say K is equals to say 9 in this example, then find a city. So from B, within 9 as distance, we may have A because this is directly as 5, then 8 which is D, and E is at 9. So these two. So for B, I'm just roughly calculating. For B, let's suppose there are 3 cities. For A, there is B and then nothing else. So in this case, maybe A will be my answer because at 9, or A, B and D actually. So at 9, A is having only 2 cities connecting with it, and B is having 3. Same way, maybe C is also having 3 and E is also having 3, I'm assuming. If this is the question, I will not be able to answer until I calculate the distance of A from all other cities, right? Then only I'll be able to say, okay, how many are within this given distance. Same thing for B I have to calculate, for C I have to calculate. So baseline, for every given node, I have to find out what is the distance, shortest distance rather, of all other nodes, if that is the game. Now, one solution can be that what I'll do is I will do my simple Bellman-Ford algorithm for every node as my source node, right? That time complexity will be same as you just multiply it with the number of vertices, whatever is the time complexity of your Bellman-Ford implementation. That is one. Another is, what we are going to see is there is a famous algorithm to solve all pair shortest path problem, and that algorithm name is Floyd-Warshall. So this is what we will learn first before we solve any question here. All right, let's talk about Floyd-Warshall algorithm first. So like we said, it is about if you need to calculate distance between all the pairs, shortest distance between all the pairs, then this is one of the algorithm. And we'll talk about where we should use it and where not, and the algorithms which we learned already, like single source one, like Dijkstra and Bellman-Ford, whether those can also be used in these cases or not. But first, let's jump into the algorithm. This is a very straightforward algorithm. So think of, you can say it's a, greedy or, okay. So think of like you are given with this graph with some weight on the edges. Like this. Okay. Now, what we know, so in this algorithm, we don't need to, let me update. Yeah, okay. So in this algorithm, we do not need to build any graph per se. That way, this will be very easy to code. Okay. But anyway, that we can ignore for now. Let's suppose we are just maintaining it in a matrix. And what we want is that from A to B via a given K, so we will check from A to B via given K whether there is a best answer or not. Okay, for example, right now to go to same node from same node, like A to A is, we know that answer is 0. So it will be same for all of these. So E to E is always 0, D to D is 0, likewise, right? Other distances in the beginning we do not know. So we can safely say that that distance is infinite. So for example, A to B is infinite. Same way A to C right now is infinite. Same way A to D right now is infinite, right? Likewise, we can fill the entire matrix. But now, in the first iteration, what we can do is we can fill that where we have the direct edges. Okay, so you can say A to B, we know the answer. A to B, the answer right now is 2. So infinite will be replaced with 2 because 2 is the shorter answer from infinite. Comparative is similarly, A to C also I know already that answer is 8. So I will update it, right? Then A to D also we know and answer is 1. A to E we do not know right now. And next is B to E. I know that B to E is 3. Then this edge is done. Then next is D to E. D to E is 10. So we will fill it here. Then this edge D to C. D to C. This one we can say is 2. And I think, yeah, C to E is one more edge which is left. C to E is 1. So initially this will be your matrix, and wherever we do not have any value, assume that's an infinity. Okay, now the algorithm says that check that if I need to go from A to B via a K node, then whether there is a better answer than what we already have. If yes, then obviously update that if we go via some other K. And what that K is, so try all other vertices which you have. Okay, so say I to J, where I to J is nothing but all your vertices we need to try. How can we try that? So we'll simply say, if let's suppose I need to try that, can I go A to E via C? Because that is directly visible into my graph, that A to E I can go via C. So A to E right now is infinite. Okay, now to go to A to E, what we will check is, can I go A to C? A to C is 8. Yes, so we have an answer. Plus, can I go C to E? So I will check C to E. Yes, I do have an answer, which is 1. So A to E, I can go in this answer, which is 9. Now 9 is shorter than what we currently have in this box. So I will simply replace it with 9. Same way I can also check, can I go A to E via B? Okay, so right now I'm obviously checking the graph and directly saying it, but this way we need to try with every vertex. Okay, so we are saying now, can I go A to E via B? So for that, what I will check, do I have an answer from A to B? So A to B is 2, so yes, plus B to E. B to E is 3. So we have an answer 5. 5 is better than what we currently have, which is 9. So we'll replace it with 5. Okay. So if you see, what we are doing here is that for every so what we are doing here is for every vertex pair that can we reach from A to another one, which is say E, can we reach there via B, comma C, comma D? And obviously we will ignore the same ones because that might have already been filled, right? All right. Now how can we write an algorithm like this? So we'll simply say for I in for every vertex, so you can say V in vertexes, then another loop, because we are saying, or you can simply say from U to V we will check. So for U as source in vertexes, then V as destination in vertexes. Can we go, that means for K in vertexes again. So this is simply 3 loops. So we will simply say, you can call it matrix where I'm saving the value. Can I go from U to V? And for that, answer should be minimum of what we already have there. It's possible that we already found the better value, right? So matrix U to V, whatever is the current value, comma, matrix U to K, like we said, can we go U to K plus matrix K to V, which is my destination. So algorithm is as simple as this, just these 4 lines. Obviously now we need to add some conditions because it's possible that U to K is infinite right now, or this is infinite right now, right? So if we'll do any addition in infinite, then algorithm will not run. Or if U and you can say these are same, U and K, in that case nothing will be wrong because by default we are filling that value to 0 in the starting. So that should be fine. So this is the base of this algorithm. If you want to see the time complexity, first we are running a loop on all the vertices. So this is V times, then again we are running the loop on all the vertices, then times we are running the loop on all the vertices. So very clearly the time complexity is your order of V cube. This is very high, right? But we'll talk about it. Can we better it, or where should we use it? Space wise, so this is my time complexity. Now space wise, here because I'm maintaining this matrix, this 2-dimensional matrix, so clearly basically we can say big of V square. Okay, so this is my space complexity and time complexity. So I will give a formal code of this algorithm, and then we'll try to solve the basic question first, that for all pair shortest path, how it is working. Then we'll try to see where other algorithms which are the one which we already did, like Bellman-Ford and all, are better than this, but still there are some questions which we should do via Floyd-Warshall rather than the other ones because of some nitty-gritties. So let's just practice the code first, which we just saw in the last section. So I'm using on GeeksForGeeks, we are directly having the question to practice the Floyd-Warshall that we will use here. So this, they are directly providing us what you can say is adjacency metrics, where you directly have the weight given that from 0 to node 1, the weight is 4. That means there is a way and the weight is 4, though this is the output. But basically for input, they have given us that from where you can go to which edge and what is the cost, and 10 to the power 8 is considered as infinity. So first we will directly use this to apply our algorithm. Like we said that for our u in the vertexes, so that was our algorithm, but we do have our adjacency matrix. So what is the vertexes here? Vertexes is nothing but 0, 1, 2, 3, which is, you know, indexes of this matrix. So I'll say that first thing first, I should know number of vertexes. So I'll call it v. V is my length of dist. Is it m into n or n into it is n into n? So yeah. Now that means I'm going in range of number of vertexes. So it will give me 0, 1, 2, 3, 4 up till number of vertexes. Second, so let's just call it n actually, as it is given as n. Second, so from u to v, in what is v? Now I will try everything from my so I will try everything in the same range of n again, right? And like I said, there will be some conditions. Now via k. So for k again is nothing but in range of n. So this is the O of order of 3, order of, you know, cube algorithm which we are writing. So first thing I'll simply do my distance of u to v I'm trying to calculate is equals to minimum of what is there already, maybe that is the minimum value, comma distance of u to k and plus distance of k to v. Now some conditions which we need to add. If u not equals to v, that means we don't need to calculate it, right? So you can say even if it is the same, it doesn't matter. So this condition I can ignore, or I can put it in this if it actually doesn't matter. Then second condition is and my distance of u to k is known. That means this should not be 10 to the power 8. So value is given 10 to the power 8. So I'll simply define a constant first and compare it with infinity. So infinity, they gave us that it is 10 to the power 8. So I can write it like this. So if my distance u to k is known, that means it should be less than infinity. As simple as that. Similarly, because I need another thing called distance k to v. So distance k to v is also less than infinity. Then only I'll be able to calculate u to k plus k to v. Is there anything else I need to check? What about k? If k is equals to u, that means it will be 0. If k is equals to v, that means it will also be equals to 0. So it doesn't matter. Yeah, that I can ignore. All right. So in the end, if I'm just done with this, so I'll have my distances. What I need to return is modify. Your task is to find the shortest distance between every, modify the distances of every pair in place. Okay, so it's an in place modification. I don't need to return anything. So let me just compile and run this one. expected output is this, my output is this, so it looks like it is fine. I'll simply submit it and let's see. For input this, my output is this. Oh yeah, what's the mistake I made? So first thing is, like we discussed, so for every k, so I'll write it again. For k in this range, I need to try for every u to v. So I'm iterating for every k, so that should be the first one rather than u. That is the first mistake. And this, like I said, u and v, if they are equal, then it will be 0, so that I can ignore just for the clean code, right? So yeah, let me just compile and run it again. And this was anyway correct. So let's just check. Yeah, all are passing. So this is the same code which we tried. There's the same code which we just learned, that for every k in basically in order of cube, we need to try for every u and v. All right. So now this was just the algorithm. Next question is, if so transitive closure, they are talking about that given a directed graph same as the previous one, determine whether j is reachable with another I. So what we need earlier, we need to figure out that from A to B, what is the shortest distance, and that we needed to find for every pair. Here, for every pair, we need to figure out whether there is a distance from A to B, and that is for every pair we need to figure it out, right? So it will be exactly same algorithm. So in fact, if I go here and I'll simply copy paste this, I do not need that infinity anymore because I'm not looking for shortest distance. So it said that there are n vertices, so obviously it will be n is given to me already. So I'll write it like this. Graph is given to me in adjacency matrix. This I'll remove. So for every k, I need to check. So do I need to check this? No. That I can remove. So they are saying one means there is a way from this vertex to this vertex, and 0 means there is no way to go from this vertex to this vertex directly. That is what is given to us. So we simply need to check if there is a distance, if there is a what do you say, path. So if there is a path, graph, if there is a distance between u to k, that means it will be 1, and there is a way. So at graph at graph k to v is also 1, then it will be 1. So what if this was already there? So now it is not minimum. So I'll say graph. Yeah. So we just need to check whether there's a distance or not. So I'll simply, if my graph u comma v equals to 0. If so far there is no, we do not know the way, then what I need to check? If graph u to k and graph k to u. So this either I can check or I can simply say graph u to v. If both are 1, k to v. If both are 1, then end will be 1. If any of this is 0, then end will be 0. So it will be 0. So if this is not, if this is 1 already, then no need to check anything. Otherwise, we will simply place it. So this time as well, do we need to return, or your task, you do not need to print blah blah blah, return the closure to the matrix. So I'll simply return this. Right now we are just running the algorithm which we just learned, and we will see where these will be useful. So we made a mistake. Graph, where is a typo? graph. Okay, this one. Okay, is the same. 1 1 1 1 0 3 1s 0 0 0. Looks like base case is running. It's compiling basically, but all the cases are failing. By default, oh, my output is 0 0 0. What's wrong here? If u to v is 0, then only I'm going inside. Okay, so what is the, oh, got that. So basically they gave the input, it's not in the correct manner, I would say. So by default, obviously every graph is reachable to itself, and that is wrong here. So they should give, so I'll simply say for I, not if. So that we will build for I in range of n, graph of I, that means distance, there should be a path from to itself, so that should be given. Yeah, okay, so there's nothing wrong in our algorithm. It's just that one edge case that they haven't given it. Cool. So far the basic algorithm we learned that this is a order of cube, where we should apply. First thing is very basic rule of thumb, that if you need to find out distance between every pair, shortest distance obviously between every pair, and number of nodes are not huge, because if number of nodes are huge, then order of v cube will definitely explode. But why this is useful? If your number of nodes are not huge and you need to pre-calculate, your prerequisite is that you should know the distance between every node, and then something you need to do on top of it, then this is best, because this is very clean code. If what we can do alternatively is we can try to run, say, the algorithms which we learned earlier, like Dijkstra, for example, right? Dijkstra is our e into v, log v. Then if we can run, so Dijkstra, for example, which is of order of e into log v, that we can run for every vertex. That for every vertex, find the distance to every other node for that vertex. So you just need to run it. What you can say is v number of times, same algorithm again and again. That also will give us the better complexity than our Floyd-Warshall. Issue is that code will be unmanageable, almost unmanageable. So if number of nodes are not huge, then better to go with Floyd-Warshall if you need all distance between all the nodes. So think of a question like this. Yeah, so this is a famous question. Course schedule is a famous question, but normally we need to do topological sorting in the famous one. This is not the one. This is the fourth variant of course schedule. Topological sorting, obviously, we will learn in upcoming videos. But here, if you see, so what is given is that you are given that to do a course, there is a prerequisite. So it is given like this. Then what you need to check is, and obviously if like this graph, right? So prerequisite of 1 is 0. Prerequisite of 2 is also 0. But prerequisite of 1 is also 2, right? If I remove 1 to 0, and you know that direct edge, then though there is no direct edge between 1 and 0, but because 1 depends on 2 and 2 depends on 0, by default that means you have to do 0 first to do 1, right? Which is, in a simple word, it is saying that there is a way from 1 to 0 that you need to figure out for all the paths. Why? Because what they are saying is that this is given. So this directed graph, you can say all the vertices are given to you, all the edges are given to you, in fact. Then after that, they'll give us the queries one after another, whether there is a way between u to v. So there can be n number of queries. So to do n number of queries, obviously what you cannot do is you cannot find the path now. Because if you will try to find the path, that means you will try to run the algorithm again and again, which will be what you can say is costly. So if my number of vertices are less, so if you see here, it's just 100. So even if I'll do cube, it will be 10 to the power 6, which is still lesser than 10 to the power 8. That means it can finish within 1 second, right? So 10 to the power, almost approximate 10 to the power 8 and lesser than 10 to the power 9 instructions run in 1 seconds. So here, so here if I calculate that my matrix, where I know that there is a distance between, so there is a path between u to v for every u and v, then I'll be able to answer every query very fast. So what I'll do is same algorithm which we just did, this one. So I'll copy this. I'm assuming LeetCode is having the graph in a better way. So prerequisites means my edges are given. So they did not even give me the graph. I need to build that graph. How can I build the graph? Okay, so let's just learn that also. So graph, I'll say default. So graph is nothing but my 2D array. So I'll say this is by default for u in range of n, if I can call this number of courses n, for v in range of n again. So let's build a graph. Graph is a 2D matrix. So by default, I'll put 0 for I in range of n, and this will be for j in range of n. So this is my 2D matrix. Now for every edge, for every u comma v, so like they give prerequisites for every u comma v in prerequisites. That means my graph u v is 1. And one more line we can copy from our previous code. That still is valid. All right. So in the end, I am having a graph which knows whether there is a way, from one node to another via any route. So now I'll try to answer all the queries. So first thing first is what I need to return is true and false. So I'll simply say answer is false, and this is length of queries. So this just made an array with all the falses. So for my query in queries, what my query is having is u and v. So I'll simply get u and v in queries. Answer better is this answer dot append whether graph u and v is equals to 1, and I just need to return answer. Let's just compile this first. For k in range of n is wrong, y o y. Inconsistent tab and spaces, okay. Some indentation mistakes. Okay, let me just compile this again. I remove the tabs. Okay, so basic compilation is fine. Let's just submit this one. Cool, yeah. So yeah, again, question like this where you need to calculate, pair of all the vertices, it's better to write a clean code like this if my number of vertices are less, and answer your queries, right? There is another question fall into the same category, evaluate design. This I highly recommend try this one if you just saw the other questions, because now you know the answer. Try to apply that algorithm here, and if you're facing any issue, just comment and we can fix it. I'll definitely reply if there are any queries in that. Thank you. Let's move to the next section.